Standard enterprise systems manage built assets by dividing their lifespans into two distinct categories: a short-term construction phase and long-term operational management. This rigid separation creates a static barrier at the exact moment a project is finished. During the handover phase, critical decision-making data, the original intent behind the engineering, is systematically lost. Over a standard 50-year asset lifespan, this data decay compounds. Operators are left managing highly complex infrastructure using incomplete records, relying on guesswork to solve maintenance problems that originate from decades-old construction decisions. Treating the initial build and decades of operation as disconnected silos creates a severe architectural flaw. Conventional static file repositories fail to solve this problem because they capture single moments in time. They cannot track the continuous behavioral evolution of an asset as it ages, settles, and degrades over decades. The Relational Ecosystem Model, or REM, establishes a new category of whole-of-life cycle asset intelligence designed to close this gap. REM's thesis: capital projects and operations are the same ecosystem, operating at different speeds. It manages assets continuously, capturing every data point from concept to deconstruction. This applies across all scales, from a skyscraper's core to a sprawling transport corridor. Unlike standard enterprise software that simply stores files, REM operates as a cognitive architecture. It is designed to interpret data and understand the entire ecosystem. Removing the artificial divide between a project's origin and its operational life allows a built environment to function as a unified, data-driven ecosystem. To understand how this cognitive architecture establishes reality, we look at the data generated by a highly complex built asset, like a skyscraper core. Traditional management relies heavily on static BIM files. BIM, or Building Information Modeling, is a digital representation of physical and functional characteristics of places. REM replaces this static approach with a dynamic, multi-layered framework. The first data vector is design truth. This layer captures the original engineering intent, structural parameters, and precise geometric constraints. The second vector, administrative truth, ingests human-generated operational data, including field notes, maintenance logs, and regulatory documentation. The third vector is physical truth. This pulls a live stream of real-world inputs, like real-time sensor telemetry and environmental conditions. REM continuously triangulates these three distinct realities into a single, cohesive, living operational model. Without this real-time tri-vector triangulation, enterprise operators cannot see the actual physical state of their building. They are managing an outdated ghost of the asset, rather than the living structure. The value of this architecture becomes clear during a high-stakes operational crisis. Consider a severe mechanical fault emerging deep inside an HVAC system 15 years after the initial asset handover. Over those 15 years, REM has systematically ingested a massive volume of data, including decades of events and the original CAD drawings. CAD, or computer-aided design, refers to the highly detailed digital models and schematics used by engineers to draft the original architecture. REM preserves the underlying logic, engineering arguments, and exact reasoning behind every historical decision, rather than just storing the final output. This interface demonstrates tracing the mechanical fault. The system analyzes immediate physical telemetry anomalies, allowing operators to pinpoint the exact location of the current stress fracture. The timeline playhead then scrubs backward through time, moving past the administrative logs filed by the construction contractor during the original build phase. The trace lands squarely on the original CAD engineering argument from year zero. This reveals the root causality, a specific design choice made 15 years ago that led directly to the modern fault. By locking these records into a continuous relational timeline, the framework maintains unbroken traceability across decades of operational noise and vendor turnover. True asset intelligence requires diagnosing exactly which component broke today, while simultaneously accessing the historical logic of why it was built that way decades ago. A pervasive industry assumption dictates that creating a successful digital twin requires seamlessly integrating thousands of disparate enterprise software applications. This diagram illustrates the inherent fragility of peer-to-peer API integrations. An API is a set of protocols allowing separate software systems to communicate. Over time, as vendors update software independently, these sideways connections inevitably break down. To solve this, REM clears the horizontal web entirely, placing all subordinate applications cleanly at the base of the architectural layout. Clean, unbroken vertical lines extend upward from each subordinate app icon to a central overarching hub called the thinking layer. In this model, REM functions as the macroscopic brain. It shifts the entire system architecture away from fragile sideways integration and toward upward orchestration. Because of this upward orientation, subordinate applications, autonomous robots, and older legacy systems do not require expensive rebuilding to function within the new architecture. These disparate tools only have one input requirement. They must be able to emit a vertical signal. It can be a text log, GPS telemetry data, or a routine schedule update. REM ingests these varied upward signals, interprets the multi-format data, and actively maintains the systemic behavioral state of the asset. This central thinking layer effectively turns every individual subordinate application into a context-aware node, completely bypassing the need for brittle APIs. Transitioning from mere software execution to central cognitive orchestration ensures the overarching architecture survives when individual software vendors inevitably change. When applied beyond a single isolated asset, we observe the true capacity of cloud-native relational foundations across a wider metropolitan landscape. Because the underlying architecture processes relational data rather than static files, the model scales across thousands of connected physical assets by utilizing cloud-native distribution. This network displays how REM asset models securely link to form a macroscopic cognitive layer. Data from a transit station interacts with the fluctuating load demands of the electrical grid, then expands outward, connecting adjacent commercial properties and shared municipal utilities. By utilizing this interconnected network, transport authorities and regional utilities can accurately model the relational behavior of entire metropolitan areas in real time. Managing assets in total isolation is highly inefficient when individual structures can act as interconnected nodes, driving coordinated city-wide efficiency. This interconnected layer produces compounding operational benefits, enabling coordinated immediate emergency responses, allowing for dynamic traffic optimization, and achieving hardened cybersecurity postures. They achieve this because they operate within a single, unified cognitive architecture with centralized visibility. Over a 50-year lifespan, physical infrastructure faces inevitable realities. Server hardware decays, software APIs deprecate, and third-party vendors frequently turn over. REM operates as a stable continuity engine, uniquely capable of surviving these technological evolutions and maintaining the operational logic over a multi-decade lifecycle. Traditional software architectures focus on task execution. REM provides the logic layer necessary to interpret environmental signals and maintain the behavioral state of the asset. By erasing the lifecycle divide and continuously triangulating design, administrative, and physical reality, REM ensures the built environment fundamentally transitions away from static, decaying infrastructure, evolving instead into a continuously learning, living, and fully cognitive ecosystem.